So continuing on with mass flow rate. Remember our friend, the specific volume, the ratio of volume per unit mass. So total volume per unit mass is little v, that is the reciprocal of density. So everywhere you have a rho, a density, you can also use a lowercase v. It's reciprocal there. Which one do you use? I don't know. It depends on what you have. Or which one do you have? Well, you need to look at the units, right? What is the dimension of that quantity? So if it's something volume per time, if the dimensions are volume per time, that tells me it's a v dot. If the dimensions are length per time, that tells me it's a speed. If the dimensions are mass per volume, that tells me it's a density. If it's volume per mass, that's a specific volume. So which one do you use? It really depends on what do you have available. And that's a realistic scenario too. You may not be able to measure the volumetric flow rate, but you can probably measure the cross-sectional area of a conduit or look it up in a table, and you probably have you might have some kind of probe or device that will be able to measure a speed or approximate a speed. So the area times the speed. These are more measurable quantities than this, or any volumetric flow rate meter is probably measuring this and this and multiplying them together for you, honestly. Okay. All right, I digress. Let's keep moving. That's mass flow rate. We also introduce the first law. Right, so if we introduce the first law, I sincerely hope you get tired of hearing me say this phrase: in minus out equals change. Energy is a conserved quantity. Most conservation laws will follow this idea that the difference between the in and the outflow is going to equal the change for our system. Conservation of energy is no different. We say that the energy, if you just look at the total energy into a system and subtract the total energy out of the system, that equals the change in the energy of our system. Okay? And so I find this is a little easier to memorize and remember than the next equation I'm going to write. Because the next equation we were going to write, we have to say, all right, what are all the ways that that energy can come into a system? Well, all the ways that energy can come into a system are going to be heat, work, and you could also have mass. So if I have mass crossing the boundary, that mass has its own energy, and that energy has to be accounted for. And all of those quantities could also go out. Right? So I could have heat out, I could have work out, and I could have mass going out. And then that's going to equal the change in the energy of the system. Well, what is the change in the energy of the system? Well, you've got internal energy, you've got kinetic energy, and you've got potential energy. So add the ins, subtract the outs, that equals the change in the total energy for our system. Now, what we normally do is we say, well, if mass is constant and it's a closed system. So if it's a closed system, the mass is going to be constant kind of by definition. I could just say if it's a closed system. If it's a closed system, well, there's no mass crossing the boundary. That's the difference between control volumes and closed systems, as you've already paused and looked up earlier if you couldn't remember. So if there's no mass crossing the boundary, then I've just got heat and work. Right? So I've got Q in plus work in minus Q out minus work out is equal to, and then if it's the same mass in each of these, because this is m times little u, this is mv squared over 2, and this is mgz. Well, if it's constant mass, I'm just going to factor that mass out of all of those. So m times delta u, little u, right? Because again, m times little u gives me big U, plus the change in kinetic energy per unit mass. So v2 squared minus v1 squared over 2, plus g times z2 minus z1 quantity. Closed quantity, closed quantity. And again, you're welcome to memorize this equation, that if I've got a closed system, that this is the first law, this is the conservation of energy principle, before it gets simplified down to a specific scenario. You're welcome to memorize this. I would suggest this is a little easier to remember, that if you add all the energy in, subtract all the energy out, that equals the change. And then you can start remembering, okay, what are the ways energy can cross the boundary? And if you'll just draw your system and say, okay, what's crossing the boundary, then this left-hand side becomes pretty easy, because it's pretty rare you're going to have all four of these. In fact, I don't know it's going to happen very often, if at all, in this class. Most of the time you'll have one, maybe two of these. When we get to Chapter 4, you guys will see on Tuesday, first thing we'll do is we'll say, well, if the system is stationary, this is 0 and this is 0. So this sum just equals m delta u if I'm dealing with a closed stationary system. But that's the future. We're not quite there yet. Okay. All right. So first law for closed systems. This is, again, Chapter 2 is kind of this introduction to the first law. To go along with that, sometimes we deal with control volumes where we've got some kind of flowing mass, so we need to deal with mass flow rate. And then the third concept that we introduce in Chapter 2 is the idea of efficiency. All right, so if we talk about efficiency, and normally we'll use the Greek letter eta to represent the efficiency. A lot of times it's kind of this idea of output over input, and that's okay. That gets us a lot of times. We saw that in the homework. It's not uncommon that we can say, well, if I've got a device where I'm trying to get output out of that device, this efficiency model makes just fine sense. It might be, another way to think about it is what you want, your desired quantity divided by the required quantity to get it. Again, if you think about what quantity do you expect to be smaller? So what is the expected smaller quantity? Divide that by the expected, whatever quantity you expect to be larger. Right? We expect every device is going to have less output than what we supply into it, especially in terms of energy. Yes, the energy's got to be conserved. What happens, that device probably is going to emit heat. And I've got a charger block here I've got my laptop plugged into, and this guy is emitting heat, right? So that tells me that all of the electricity coming in here is not the same as all the electricity going out there. There's a difference. That difference can be measured on the efficiency. I can say, well, take the DC electricity coming out of it, right? And that's my numerator. I expect that to be smaller. Divide that by the AC electricity going into it, right? Efficiency is always, a true efficiency is always between 0 and 100%. Right? And it is going to be unitless. What that means is I'm going to have the same units on top as I do on bottom. I've got to have the same dimensions, and I've got to convert the units to be the same. Right? So I can't put PSI up here and then watts down there. That's not, no, that doesn't work. I've got to get this to the same dimensions. This has to be the same dimensions. I'm going to be comparing energy to energy or power to power. Okay. Let's see. There's another thing that comes up. What does this mean? Adiabatic. If you don't know what that means, pause right now and go find it. Seriously, go. Just pause, take you a moment, look it up in your notes, look it up in the book. Make sure you know what that word means for the entire class moving forward. Go ahead and pause. Okay, you back? You know what adiabatic means? Okay. I'm going to expect you to know what adiabatic means. Let's see. And what else? Those are the main things I can think of, right? Know what the units, expected units of power and energy would be, right? BTUs, joules for energy, or watts and horsepower for power, or energy rates. Okay. Okay, I guess I've still got room down there, right? So that's the big stuff out of Chapter 2. So that's Chapters 1 and 2, kind of quickly in a nutshell. if we talk a little bit about Chapter 3, so I'm not going to go super in-depth in Chapter 3. We've already talked a little bit about this, or just recently talked about this, and you just finished up a homework assignment. But if we talk about Chapter 3, it is, again, we're talking about properties of pure substances. Excuse me. And the first substances that we talk about are going to be water and R134. Right? We're going to talk about the saturation tables because we talk about the different phases of matter. So we'll use tables to talk about the energy, the U values, the internal energy. We can't measure the internal energy directly for a system, but what we can do is if I know that the system contains water or R134, given a couple of properties, I can go figure out what the U value for that water and R134 would be at state 1, and then after we add some heat and pull some work, I can figure out what the properties are at state 2. And so in Chapter 4, we're going to expect you know how to go find U values, and we're going to actually work with this equation, knowing that you know how to find U values now, and solve for an unknown. That's where we're headed. To get there, we got to make sure you know how to use these table properties, or figure out what table properties are. So, using property tables, and I went into a big spiel about, you know, hey, you're going to go through this process. You want to have this handy, and I'm not going to promise I'm going to write it exactly verbatim as I did last time because I don't have those notes immediately handy here. But after you go through this process, probably 100 times or so, the first 100 times, you'll get to where you won't have to look back at this list. But until you get up to about 100 times doing it, and you might want to look back at this list. And then the next, you know, 200 to 300 times throughout the rest of the course that you go through this process, it'll become second nature. You won't think about it. Using property tables, step 1 is, what do we say? Identify your substance. Sorry, I'm trying to write fast, and that's making things worse than it normally is. Identify your substance. And for us, we're really going to focus right now on water and R134A. So a little bit later, we're going to talk about what do we do if we have some gases. And then after that, we'll talk briefly about what do we do with solids and liquids. But for now, we're going to focus on water and R134A for exam 1. Okay? So identify your substance. Those are going to be the two that I'm looking for here. Step 2 is identify known properties at each state. Now, a lot of times in Chapter 3 problems, you may only have one state. Now, there are some of the problems where they'll ask you about, you know, you have these properties, and then we go through heat is added, or we go through some kind of process, and now these are the properties. So what they're telling you is you might go between two different states. So at each individual state, make sure you record the properties that you know. And then for water and R134, you need at least 2. Now, we're going to talk about gases a little bit later, and really all I need to know for gases or solids or liquids is the temperature. But for water and R134, I need at least 2 properties. Okay? And we'll talk about what those combinations look like in just a second. We've seen that before. Step 3 is determine the state. And I like to put that in layman's terms and say, well, that's which table in which row, or you might be between rows, so which table or which rows. That's how I like to say that. Right? Determine the state, and we've said, well, you got to use the appropriate table for the appropriate units, right? And so those of you that kind of went the easy way on Chapter 1 homework and didn't do the problems in the English units, you converted everything to metric. Guys, that's not going away. You're going to have to learn the English set and how to work with it, because you're going to really make your life difficult using property tables if you have to convert everything to metric, because you're not going to line up nicely on rows all the time. Okay? All right, next video.